So we're going to look at the key, or going through the solutions to the last exam that you took. In the first problem, you have a polynomial f of x equals 2x to the fourth minus 9x cubed plus 2x squared plus 9x minus 4. And you want to answer the following questions. So we're going to find all the zeros of the polynomial. We're going to use at least two different rules to help us find the zeros of the polynomial and state which rules you're using. So I prefer the rational zero theorem, or rational root theorem, this P over Q. Well, if I look at my values of P are the factors that go into your constant. So this is plus or minus. Things that go into 4 are 1, 2, and 4. Q are factors of our leading coefficient of 2. Which is 2 in this case, so 1 and 2. So now looking at P divided by Q, this is plus or minus. 1 divided by 1 is 1, 1 divided by 2 is 1/2. 2 divided by 1 is 2, 2 divided by 2 is 1. I don't have to list that zero or that possible zero again. Now going through with 4, 4 divided by 1 is 4, and 4 divided by 2 is 2. So now I would use synthetic division to help me see which one of these, if any of them, are zeros of the polynomial. And so we're going to list the coefficients up here: 2, -9, 2, 9, -4. And see if we get a 0 as our remainder, the last number. So bringing down our first number, we have 2. 1 times 2 is 2. -9 plus 2 is -7. 1 times -7 is -7. 2 minus 7 is -5. 1 times -5 is -5. 9 minus 5 is 4. 1 times 4 is -4. I'm sorry, it's +4, but adding that to -4 gives us our 0. So x equals 1 is a 0. Some of you are putting that x plus 1 was the factor. And that's not the factor, it is x minus 1 is the factor when x equals 1 is the 0. We have brought this down to now a degree 3 polynomial right here. So this is the same thing as going 1 degree less than the horizontal row on top. That's going to be a cubic. So this is 2x cubed minus 7x squared minus 5x plus 4. And so let's look at zeros of this, because zeros of this polynomial will also be zeros of f of x. And so let's write our coefficients down and test more values. So coefficients of this is 2, -7, -5, and 4. And let's test maybe, I don't know. I do know. Let's test -1. So let's bring down 2. So I have a 2, -1 times 2 is -2, -7 minus 2 is -9, -4 times -9 is +9, -5 plus 9 is 4, -1 times 4 is -4, and this gives us 0. So I know that x equals -1 is a 0, which makes that x plus 1 is that factor. We now have a quadratic. This is the same thing as 2x squared minus 9x plus 4. We want to know when is this piece equal to 0. And so we can factor this. I'm going to just do it by guess and check. So two things that multiply to give me 2x squared are 2x and x. And I need two numbers that are going to multiply to give me 4. And so how about 2 and 2? No, actually, how about 4? I notice that this is negative, so they both need to be negative. So how about -4 and -1? So let's just make sure that that's correct. So -4 times -1, that's my +4 up here. That's good. I need to make sure my middle term is good. So this is a -8x minus a 1x is my -9x. So that's also good. So I know 2x minus 1 is equal to 0. When x is equal to add 1, divide by 2, 1/2. And x minus 4 is equal to 0. Add 4 to both sides, x equals 4. So the zeros of our polynomial are x equals 1/2, 4, -1, and 1. Wanted to know what rules I used. I used the rational zero theorem. And I used synthetic division to help me solve this. So some of you had used Descartes' rule signs as a way to help you, and that was fine. Some of you said, some of you had said the quadratic formula. And actually now thinking about it, I guess that is a rule that you're using. Some of you had used it on the quadratic piece to figure out what those zeros were. And so I guess I'll go back and give you that 0.5 point back. So that would also be correct. Part B wants us to rewrite f of x as a product of linear and or irreducible quadratic factors. Well, we already did pretty much most of the work here. We have these factors and we have these factors. And so the two, we could rewrite f of x as a product of 4 linear factors. It doesn't matter order. So the quantity x minus 1 times the quantity x plus 1 times the quantity 2x minus 1 times the quantity x minus 4. Okay, so that was problem 1 on the test. Let me see if there's any questions before I move on. So problem number 2, we're given that 5i is a 0 of f of x equals x cubed minus 8x squared plus 25x minus 200. Find the remaining zeros. So there's a couple ways that we can do this. One way is knowing that this is a 0 of our polynomial. We know that if we use synthetic division, so 1, -8, 25, -200. If we use synthetic division, that we should get back a 0 for a remainder, and that this will be 1 degree less. And so we're breaking it down, our polynomial. If 5i is a 0 by the complex conjugate pair theorem, -5i is also a 0. So doing it this way, we're bringing down a 1. 1 times 5i is 5i. So you need to be careful here. We're adding a real number and imaginary number. Remember, we're adding the real parts together and the imaginary parts together. So there's no imaginary part for -8 and there's no real part for 5i. So this is going to be written as -8i plus 5i. So I need to multiply 5i times that. I'm going to do this on the side work. So 5i times -8i plus 5i. Oops, sorry, I just made a mistake. This should just be -8 plus 5i. Let me change that. So excuse me, let's distribute the 5i to each term. So 5i times -8, that's -40i. And then 5i times 5i. Well, 5 times 5, that's +25. And I squared, recall, was -1. So times -1. So we really have -25 minus 40i. So let's put that below the next number. So -25 minus 40i. So summing the real and the imaginary parts here, we just get back -40i. So 5i all times -40i. Well, 5 times 40, that's negative 200. And I times I, that's I squared, which is negative 1. So this is going to give me a positive 200. And this gives me 0, like I said I should get. So now we can do the same thing, but let's use this bottom row. And we know that, again, negative 5i should also be a 0 by the conjugate pair theorem. So bringing down 1, we have 1 times negative 5i is negative 5i. Combining this, we have negative 8. Negative 5i times negative 8, that's positive 40i. So that's 0. This time we had a quadratic. This time we have a linear function. And so this is x minus 8. So we're looking at when is x minus 8 equal to 0? And this is when x is equal to 8. So our zeros, our remaining zeros are negative 5i and 8. So there were multiple ways to approach this. One of you had noticed, and if I had noticed this, I wouldn't have given it to you like this, but we could use factoring by grouping here. So we could have factored out an x squared there, all times the quantity x minus 8. Here, 25 minus 200, we could have factored out a negative 25. And doing that, actually, or negative, yeah, a positive 25. And so that would give us x minus 8. Factoring out x minus 8, all times x squared plus 25. We're looking at when is this 0? Well, x minus 8 is 0 when x is 8. And x squared plus 25 is 0. We're using the square root property. If we subtract 25 on both sides and then take the square root, we get x is plus or minus the square root of negative 25, which is equal to plus or minus 5i. There was one other way that you could have approached this, where we could have looked at our factors. So 5i was a 0, x minus 5i is a factor. We also know that x plus 5i is a factor. If we distribute this out, difference of squares, this is x squared plus 25. Then we could have used long division here. And so using long division into this x cubed minus 8x squared plus 25x minus 200. Plus 25x minus 200. So we're looking at the first term, x squared, thinking to ourselves, x squared times what gives us x cubed? Well, that's just a single x, and then we had to distribute it. So this gives us x cubed, x times 25, so that's plus 25x. I put this underneath like terms. Remember, we subtract this off. And so x cubed minus x cubed cancels. Let's bring down the negative 8x squared. And then we have 25x minus 25x. Those cancel. And then let's bring down the minus 200. So now again, you're looking at x squared times what is negative 8x squared, which is negative 8. Distributing it, we get negative 8x squared. And negative 8 times 25, that's negative 200. So subtracting this off, changing the signs, we get back 0, which we knew we should get, and something was wrong if we didn't get it. And so if we know that x minus 8 is a factor, then x equals 8 is a 0. And so again, we get the remaining zeros are -5i and 8. So there's different methods of going about solving that. I kind of wanted to go through each one because they kind of bring in different topics that we have used throughout the semester. With long division of polynomials or adding and subtracting real and complex numbers, etc. So we have f of x equals 1 over x plus 3 and g of x equals 2 over x. And we want to find the domain of the composite function, f of g of x. And so let's look at g of x and the domain of that. The only trouble spot for g of x is when our denominator is 0, the value of x which set the denominator equal to 0. And so x cannot be 0. So it's all real numbers but 0. Let's look at the domain of f of x. We need that domain to help us figure out the domain of that composition of the function. And so the domain of f of x, again, we can't have the denominator equal 0. The denominator is going to equal 0 when x is -3. So x can't be -3 for the domain of f of x. It's this composite function though, because g of x is that inner function. And so when we don't want some input that we're plugging into g of x that will give us an output of -3. So we're worried about when is 2 over x equal to -3. And we'll need to exclude that value of x. And so we can multiply both sides by x to clear our fraction. And we can do that because this is an equation. Divide both sides by -3, we get x is equal to -3/2. Okay, so x can't be -3/2. And so we need to look at the domain of g of x. So those are the values we're plugging in, and the domain of the composition. And so the domain of the composition are all real numbers. So I can state this from -infinity to -3/2. I'm not including -3/2, so I'm going to put parentheses, union -3/2 to 0, union 0 to infinity. So that was one way to state it. You could have just said it's a set x such that x is not 0 and x is not -3/2. Okay, so our next example or problem is the following. Okay, so the next problem, we have a rational function and we want to figure out what our vertical, horizontal asymptotes are. Our rational function is f of x equals x squared minus 4 all over x squared minus x minus 2. So to figure out what our vertical asymptotes are, we want to factor both our numerator and our denominator. And so looking at this, factoring our numerator, it's a difference of squares, factors as x minus 2, x plus 2. It doesn't matter order. And then I notice x squared minus x minus 2 also factors as x minus 2 all times x plus 1. So our domain, x cannot be 2 or -1. But if we look at this for our vertical asymptotes, we are not going to include the value which sets both the numerator and denominator equals 0. So the only vertical asymptote that we have here is x equals -1. Horizontal asymptote has to do with the degree of the numerator and degree of the denominator. And looking at this, the degrees are the same. And so if they're the same, we look at the leading coefficient of the top, which is 1, divided by the leading coefficient of the denominator, which is 1. And so 1 divided by 1 is 1. The only time we have a slant asymptote is when the degree of the numerator is larger than the denominator. So if we have a horizontal, we don't have a slant. So this is not available, or empty set, or none, whatever you want to write. The next part is find the X intercepts. And so remember, X equals 2 is not part of our domain. So only value that's going to set the denominator equals, the numerator equal to 0 is when X plus 2 equals 0. So this would be X equals -2. We can find the y-intercept by plugging in 0 for X. And so looking at f of 0, we get -4 over -2, which is 2. So we want to plot some of our points, or asymptotes and everything, and see what we get. So we had a vertical asymptote at -1. I'm just going to put a dotted line there. And we actually had a horizontal asymptote at this x-axis. Oops, sorry, no, we didn't. Get rid of that. It was y equals 1. So we have a horizontal asymptote, denoting it by this. Okay, let me plot my intercepts. And from there, I pretty much know what my graph is going to look like. And so if we let, let's see, x equals -2. So we have an x-intercept here at -2. And we had a y-intercept at 2. So knowing that, I know that my piece to the left-hand side of my x equals -1 will look like the following. Because I can never cross a vertical. It's possible to cross a horizontal, but never a vertical. And knowing where my asymptotes are on the right-hand side, I know I have something that looks like this. The thing is that at x equals 2, I'm going to have some open circle. I'll figure out where that is in a second, because that's the value which sets both the numerator and denominator equal to 0. So the next question asks, does f of x have a hole in the graph? If so, where? So the hole is going to exist, the value which sets both the numerator and denominator equal to 0. And you're going to find that by let's looking at the reduced version. So when we canceled those factors, we were left with x plus 2 all over x plus 1. And if we go in here and we plug in 2, wherever we see an x in that reduced factor, we get 2 plus 2 all over 2 plus 1. So this gives us back 4/3. So we have an open circle at 2 4/3. And the last part says find when f of x is greater than or equal to 0. And so if you had the graph wrong while you did this, I was grading this based off your graph. And so if you had gotten this correct based off your graph, I gave you all of the credit. Some of you were not right, though, based off of some of your graph. So I knocked some points off. But we're looking at when is f of x greater than or equal to 0. So we're looking at when is our y value. So when is that graph above the x-axis? And we're looking at the x values for the y value, which is above the x-axis. So notice it's above the x-axis here. So we have value from -infinity all the way to -2. And because the equal portion is there on the inequality, we're going to have a bracket in there. union. And so notice that it's above the x-axis everywhere on the right-hand side of x equals -1. The only thing is it's undefined at 2. And so we want to write that when we're putting this in. So this is going to come from -1, not including, because that's a vertical asymptote, to 2, parentheses, union 2 to infinity. And the next problem, it says write the expression natural log of x times the cubed root of x squared plus 1. That's all over x minus 3, where x is greater than 3, as a sum and or difference of logarithms. Express powers as factors. And so let's rewrite this a little bit. This is the same thing as the natural log of x, the cubed root of x squared plus 1. Remember, we can rewrite radicals as powers. So this is the same thing as x squared plus 1 raised to the 1/3 power, all over x minus 3. And so we can break this down. Division, we do subtraction. And so this would be the natural log of our numerator, x all times x squared plus 1 raised to the 1/3 power, minus the natural log of our denominator, x minus 3. Here and here we have multiplication. To break down multiplication, it's addition. So we have the natural log of x plus the natural log of x squared plus 1 raised to the 1/3 power, minus the natural log of x minus 3. And the last piece is any exponent we're going to bring down as a coefficient in front of our log. And so we have the natural log of x plus 1/3 natural log of x squared plus 1 minus the natural log of x minus 3. Okay, so the next question says, graph each equation and find the points of intersection, if any. We have y is equal to 4 over x minus 3, and the circle x squared minus 6x plus y squared plus 1 equals 0. So first thing I would do is put this circle in standard form so that we know where our center is and where our radius is, so that will help us graph it. So we want to complete the square on our x terms. We don't need to do that on our y term, and we want to get the constant to the other side. And so x squared minus 6x. I notice that I'm going to have to add the number to make this a perfect square. So it's half of -6, which is -3, and then square that number. So -3 squared is 9. And then we have that plus y squared equals, well, I'm subtracting 1 on both sides. And if I added 9 on the left, I have to add it on the right. And so the first 3 terms is now a perfect squared. We have x minus 3 quantity squared plus y squared is equal to 8. So I can tell what my center is. It is 3, 0. And my radius is square root of 8, or 2 root 2. So let's graph that. So 2 root 2, or square root of 8, that's a little more than 3. And so I'm just going to go up, down, left, and right a little more than 3 from my center to get my circle. Okay. So we got our circle here. Pretend. And now let's look at our graph of y equals 4 over x minus 3. And so this is graphing a rational function. Or you can think of it as transformations on 1 over x. This minus 3, right, would transpose that graph over to the right 3 units. Or noticing this, I notice I have a vertical asymptote at x equals 3. So I'm just going to do a dotted line there. And so I also know that I have a horizontal asymptote at y equals 0. So I'm just going to plot a couple points on the left and right of my positive x equals 3 just to get a couple points and to plot them and see what the graph looks like. So if I looked at, let's say y sub, let's look at 2. So if we plug in 2 wherever we see an x here, we get 4 over 2 minus 3, which is 4 over negative 1, which is negative 4. So at 2, I have a point at negative 4, or I have a point at 2, negative 4. Okay, so knowing that, my graph is going to look something like this. And I don't know actually if it's going to cross it or not, or if it's going to cross it more than once. And I technically won't know that until I solve for those points. But I know that technically that this is going to look like something like this. Let's see. At least on that side of 3. Now, if I look at another point, so maybe x equals 4, so y sub 4. So plugging in 4, wherever I see an x in here for this value of y, I got 4 over 4 minus 1, which is 1. So 4 over 1, I'm sorry, 4 minus 3, which is 1. So we have 4 over 1, which is 4. So we have a point at 4, 4. So knowing that, having a point at 4, 4, I know my graph looks something like this. I did want to plot those together. I'll do that in a second, just so I know if it's crossing more than once, or just or where it's crossing. So now we want to look at where are the points of intersection. I would use what we had used or found over here for our circle. So we had found our circle in this form of our equation, x minus 3 quantity squared plus y squared equals 8. I'm going to use my substitution method, and wherever I see a y in this circle, I'm going to plug in 4 all over x minus 3. So we have, rewriting this, x minus 3 quantity squared plus y squared. So I'm going to put a parentheses, quantity squared equals 8. And in that parentheses, we're putting what y is, which is in our case 4 over x minus 3. So let's simplify this a little bit. So we have x minus 3 quantity squared plus 4 squared. So let's just square our numerator to denominator. So 4 squared is 16 all over x minus 3 quantity squared equals 8. So now we have a rational function. And so we can deal with that rational function because it's an equation. We can clear the fractions by multiplying by our LCD. And our LCD is going to be our denominator, which is that x minus 3 quantity squared. So I'm going to want to multiply that by both sides of my equation. And so when I distribute it over here, I have an x minus 3 quantity squared times an x minus 3 quantity squared. That's going to give us an x minus 3 raised to the 4th power. Plus, so distributing this x minus 3 quantity squared over here to the 16 over x minus 3 quantity squared, those x minus 3 quantity squares cancel, just leaving us with 16 equals 8 times x minus 3 quantity squared. So if I set this equal to 0, I'm going to then use substitution to help me solve this. And so let's move over that 8 times that x minus 3 quantity squared by subtracting it on both sides of our equation. And so we get x minus 3 raised to the 4th power plus 16. Actually, I'm going to rewrite the order a little different. So minus 8 all times x minus 3 quantity squared plus 16 equals 0. So using substitution, I'm going to choose u to be x minus 3 quantity squared. And if that's the case, then, and remembering that power to power is multiplication, this is the same thing as u squared minus 8u plus 16 equals 0. So this is now factorable. There's two numbers that multiply to give us positive 16 and add to give us negative 8, which is negative 4 and negative 4. So u minus 4 is equal to 0 when u is equal to 4. But we want to know what x is and not u. And so we're going to plug that value in for u. We're looking at when is x minus 3 quantity squared equal 4. We can use that square root property. So this is x minus 3 equals plus or minus the square root of 4, which is 2. So if we add 3 to both sides, so 3 plus 2 is 5. So we want to have a value at x equals 5. And adding 3 to negative 2. So 3 minus 2 is 1. So there's two places where it's going to, the graphs are going to intersect. That's just the x value though, and we want the y value also. We want to know what that point is. And so we have to use one of our equations. So let's use that equation y equals 4 over x minus 3. So if we look at y sub 5, plugging in 5 wherever we see an x, this is going to be 4 over 5 minus 3, or 4 over 2, which is 2. Okay, so I know I have a point at 5, 2. My graph is not good. Okay, right here, 5, 2. And again, I know what my graph looks like on that side, so it's going to look like this. And now let's see what's happening when x is 1. So if we plug in 1 wherever we see an x here, we get 4 all divided by 1 minus 3. So 4 divided by negative 2. So 4 divided by negative 2 is negative 2. So we also have a point at 1, negative 2 right here. So our graph looks like this. So points of intersection again are 5, 2, and 1, negative 2. Okay, so notice that within this thing, or within this problem with finding those intersections, you had to use the method of substitution. Then we needed to use, well, substituting just what the one equation was in. And then we used u substitution. We solved for a rational equation. Oops, right over here. We had to solve by taking the square root of both sides here. So there was just so many different rules that we used in that one problem. Okay, so write out the partial fraction decomposition for the expression x squared minus x minus 8 all over x plus 1 times x squared plus 5x plus 6. You need to make sure that the denominator is factored as far as possible. And in this case, it is not. And so let me just rewrite this a little bit different. So we have x squared minus x minus 8 in our numerator. Our denominator is x plus 1. But this x squared plus 5x plus 6 can factor as x plus 2 times x plus 3. So depending on what type of factors we have in the denominator depends on how we rewrite this. They're all linear factors that are only appear once. And so to rewrite this, we're going to do a over x plus 1 plus b all over x plus 2 plus c all over x plus 3. We can now clear our fraction by multiplying through by our LCD. Our LCD is x plus 1 all times x plus 2 all times x plus 3. So x plus 1, x plus 2, x plus 3. So on the left, we're left with x squared minus x minus 8 is equal to, well, when we distribute, the x plus 1 is going to cancel when we first distribute it for the first fraction. And so we're left with a times x plus 2 times x plus 3 plus b all times. So when we distribute this grouping to that second fraction, the x plus 2s are going to cancel and you're going to be left with x plus 1, x plus 3. Plus c, distributing that to the third fraction, x plus 3 cancels, so we're left with x plus 1, x plus 2. So I could technically distribute each one of these and simplify and then look at the coefficients. Or I showed you guys a trick where we can let x be particular numbers and solve it that way. So let's how about start with x equals -1. If we go in and we plug in -1 wherever we see an x, notice this b over here and this c, those are going to go away because we have -1 plus 1 in those factors, and that's 0. 0 times anything is 0. So if we plug in -1, so plugging it in on the right-hand side, we get -1 squared, which is 1, minus a -1, so that's plus 1 minus 8, is equal to, and now let's plug in -1 wherever we see an x here. So this is equal to a times, so -1 plus 2, that's going to give me 1 for that first factor, and -1 plus 3, that's going to give me 2 here. So we have 2 minus 8, -6 equals 2a. Divide by 2, I get a is -3. So I want to do the same sort of idea to get my values for b and c. So now let's look at, how about x plus 2? So if we go in and plug in wherever we see an x, x plus 2. And so we can plug in -2. Wherever we see an x, that first piece, those are going to go to 0, or that a is going to go to 0 and c is going to go to 0. All we're left with is, in this case, on the left-hand side, -2 quantity squared, which is +4, minus a -2, so plus 2, minus 8. This is equal to, so we're going to be left here with b all times -2 plus 1, so that's a -1, and -2 plus 3 is +1. So we have 6 minus 8 is -2 on the left equals -b. So in here, b equals 2. And one more case, let's let x equal -3. So this a is going to go away, this b will go away. And now let's start plugging it in on the left-hand side. So -3 quantity squared is 9, minus a -3, so +3, minus 8 is equal to c. So -3 plus 2, that gives us -2. And -3 plus 2 is -1. So 9 plus 3 is 12, 12 minus 8. So that gives us +4 equals 2c. So c here is 2. So we know what a, b, and c are. So we now know what our equation is. And so we can say that this is the same thing as a, which is -3 all over x plus 1, plus b, which is 2 over x plus 2, plus c, which is 2 over x plus 3. And that's the partial fraction decomposition. And so you could have done this differently if you had expanded. You're going to have a system of equations, and then you could use that. You're going to have a system of, I think, 3 equations, 3 variables, and then you can use matrices if you wanted to solve that. Okay, so the last question says that identify each equation. If it's a parabola, give the vertex, focus, directrix. If it's an ellipse, give the center, vertices, and foci. And then if it's a hyperbola, give it center, vertices, foci, and asymptotes. So looking at the first equation, I can tell that that's a parabola, and I can tell it's a parabola either facing to the left or facing to the right. And so I want to put it in the form where I have a perfect square of my y terms and the x terms on the other side. So rewriting this, I have y squared plus 2y. So thinking of what I needed to add to make this a perfect square. Well, dividing 2 by 1, I'm sorry, dividing 2 by 2 is 1, and 1 squared is 1. Is equal to, I'm going to add x to both sides. So this is x. And if I added 1 to the left-hand side, I have to add it to the right-hand side. And so this left-hand side is a perfect square, and this is y plus 1 quantity squared is equal to x plus 1. Okay, so our vertex, it's the opposite sign. And so h is with our x value, so that's -1, and k is with our y value, and that's -1. So we have a vertex at -1, -1. We have a parabola, I didn't state that or write it. I need to figure out what p is. And so remember that this was 4p or 4a in front. And that was going to help us find the foci and the directrix. Your book used a. So we know 4a equals 1. And so a is equal to 1/4. So on my parabola so far, and I know that it's facing to the left, it's going to look like this. And so to get my directrix, I'm going to add 1/4 to the x value of my vertex. And so my directrix is at -1 plus 1/4, -1. So -4/4 plus 1/4 is -3/4, -1. That's not our directrix, that's our focus. I'm sorry. I'm a little out of it still. This is their focus. Our directrix is a line. Our directrix, when we're going to get that line, and it's x equals because it's a vertical line. And so we have x is equal to, and to get to there, we're going to subtract 1/4 from the x value of our vertex. So it's -1 minus 1/4. Our x is equal to -5/4. That's our directrix. So foci and vertex, which is a parabola. Okay, so the next one I can tell is an ellipse right away because we have an x squared, a y squared, and the numbers in front of the x squared and the y squared are different, but they're both positive. They're both the same sign. If they were opposite signs, then it would be a hyperbola. So I already have them grouped. So let's rewrite this. We have x squared plus, in order to complete the square, our coefficient in front of the y squared has to be 1. And so let's factor out a 3 here. We have y squared minus 4y. We're going to add something in here to make this a perfect square. And our parentheses equals, I'm going to subtract 9 plus whatever I added to this left-hand side, I have to add to the right-hand side. But I have that 3 coefficient out front of my parentheses. And so really it's going to be 3 times whatever I had added. So figuring out what that number is to make that a perfect square, half your b value. So -2 divided by 2 is 2, -2. And square -2, we get 4. So we're going to add 4 to both sides. Well, not technically, 12 on the other side. And so rewriting this, we have x squared plus 3. This is now a perfect square inside the parentheses. So that would be y minus 2 quantity squared is equal to -9 plus 12, which is 3. Now let's divide all sides by 3 to put it in that standard form of an ellipse. And so we have x squared over 3 plus y minus 2 quantity squared all over 1 is equal to 1. So for the ellipse, I can tell what my center is. My center is going to be 0, 2. I can tell it's going to be elongated. The vertices, are going to be it's going to be elongated. The major axis is going to be parallel to the x-axis. So it's going to look like something like this. And so I know I'm going to need to, let's figure it out. Looking at the larger number, which is 3, my a squared is 3. So I know a is √3. So I need to add √3 and subtract √3 from the center, and that's the x value. And so my vertices on my major axis is going to be -√3, 2, and +√3, 2. But I also want to get the vertices on my minor axis, so that will help me graph it if I needed to graph it. And so I need to look at my b value. My b value, b squared is 1, so b is 1. So I want to go up 1, down 1, and that's going to affect the y value of the center. And so adding 1 and subtracting 1 to 2. So 0, and then we have 2 minus 1, which is 1, and 0, 2 plus 1, which is 3. The foci, those are always on the major axis, and we need to go over c units. For a ellipse, it's different for on hyperbola, c squared is equal to a squared minus b squared. So I know c squared is equal to, well, a squared is 3 minus b squared, which is 1, c squared equals 2, so c is equal to root 2. These are distances, and that's why I am ignoring the negative when taking the square root. Okay, so adding and subtracting root 2 from my x value of my center. So that would give me negative root 2, comma 2, and positive root 2, comma 2. Okay, so we've listed everything it asked us to find once we identified the shape, which was an ellipse.